If not, write in the chat. So here we are in a very special place for us. This is one of the tunnels of Virgo. There are two of them because, as I said, there are two arms. Where inside of this tunnel, we have this very big tube. I don't know if you realize how big it is. And inside of here, the laser light of Virgo travels. So some information about the place where we are. Each of these tunnels is 3 kilometers long. That is quite an impressive length. I'm sure you can't think of a lot of buildings that are 3 kilometers long. This is also a technical challenge because, as you know, the Earth is round, it's not flat. So over 3 kilometers, the Earth will start curving a bit, while the laser light moves straight. So we have to make a tunnel that is straight while the Earth curves underneath it. So basically, the end of the arms of Virgo will be a bit taller from the ground than the center. This is one of the technical difficulties. Another technical difficulty is that, as I told you, we are near Pisa. You may have heard of Pisa, those maybe the Europeans more, but I think maybe everyone might have heard of Pisa because of its leaning tower. Why does the Tower of Pisa lean to the side? Because the ground is not very firm. It has a bit of it goes down a bit over time, and so that's what happened to the Tower of Pisa, and that's what might happen also to the tunnels of Virgo. But it doesn't, because now we have some more technical knowledge than the people who built the Tower of Pisa did. So this entire tube is held up on these blue structures, and these structures can be adjusted. So measurements are done periodically to make sure that all the tube is still level. And if it's not, they can be adjusted a bit. So what happened to the Tower of Pisa will not happen to the arms of Virgo. So why a tube this big? How big is the laser of Virgo? This is a question that we often get. So not this big. It's not that big. The size of the beam really depends on where we measure it, but there are some points at the beginning where it's a few centimeters big. So you have to imagine a laser beam about this big. But inside the arms, it gets a bit bigger. So it's about this big, which is quite impressive because I'm quite sure that you haven't seen a laser, like a laser pointer that with that big of a beam. But still, definitely not this much big. So it wouldn't need a tube this big. The reason why it is of this size is because the laser has to travel in vacuum, and it has to never encounter anything on its path. So, because if it did encounter something, the light would scatter. It would start going all sorts of places. So the tube is big enough that the laser can travel through it and not ever see the sides of the tube. And also, as I said, it is in vacuum. What does that mean? It means that we pump the air out of the tube. And so there is no air, and there are very, very, very few particles. That is a level of vacuum even bigger than the vacuum that is, for example, between the Earth and the Moon. That is more dirty than the vacuum of Virgo. The vacuum of Virgo is a level of vacuum similar to deep space. So if you could travel outside of the solar system, you would find a vacuum similar to the vacuum of Virgo. And actually, Virgo is the biggest volume of vacuum in Europe. And it is only second in the world to the volume of vacuum of LIGO, the other gravitational wave detectors, because the LIGO detectors have 4 kilometers arms instead of 3. So their level of vacuum, their volume of vacuum is slightly bigger than that of Virgo. But the two LIGOs and Virgo are the biggest volumes of vacuum on Earth. And again, this is because the light must not ever scatter. It must never encounter an obstacle, because if it does, it will start going in unforeseen directions. And this will ruin the measurements, of course, because what matters to us is the length of the path. So the length of the path must be exactly that. It must not be disturbed. So maintaining this level of vacuum is very hard. Making it took years in the first place, and this same vacuum has stayed that way for the past 20 years, more or less. It stays that way because along all of these 3 kilometers arm, we have pumps that continuously pump air out of the tunnel. And all the layers around it are, again, to protect this vacuum and also to allow us, if we need to make the tube, because I can show you where the tube is. It's this one. It's this brown one. All these protections are something that we may need in order to cook this tube. Why should we cook it, and why is it brown? So first of all, it's not brown because it's bronze. It's not bronze. It's stainless steel, but it's brown because it has been cooked once. And this cooking means that it has been brought to very high temperatures by making a current run through it. And it has been brought to these temperatures because when you do that, it will release all the particles, all the imperfections, all the impurities. And this may need to be done again. And if this needs to be done again, we already have a cover on it that will help us cook it, bring it to very high temperatures. This is the same principle of when you lay in bed and you put your cover on you, especially now that it's very cold, at least in this part of the world. And you put a cover on you so that the heat that you're producing doesn't go away, it doesn't get wasted. And this is the same principle of this cover that is on the arms of Virgo. While I think of whether I have something else to say, I ask you if there are questions. Yes?
Question. How do you manage to have the same arm length at the precision of 1,000 of a proton diameter?
Yeah, that is actually the hardest part. That is very hard. And the way that is done is to be able to control those mirrors very, very precisely. We keep them, as we said before, suspended on this chain of pendula that prevents them from vibrating when the ground vibrates. So we put them, first of all, we put them more or less in the right position. Then we are able to control them through the magnets that we were talking about before. And we keep them from vibrating through this very, very, very high chain of pendula. Of course, this is not a perfect system. We still have moments in which the mirrors are not exactly where we want them to be. It's still a very work in progress sort of a mission. So the goal is to be able to keep the mirrors exactly where they should be, 24 hours a day, 7 days a week, all year, so that we can collect data and see gravitational waves. Of course, this doesn't happen 24 hours a day, 7 days a week, because again, there can be thunderstorms, there can be an earthquake, there can be something that makes those mirrors vibrate, and we may lose the perfect functioning of the interferometer for a while. That is also why it's important to have 3 of them, because maybe Virgo may have some problems one evening, but the LIGO detectors are working well, or one of the LIGO detectors might have a problem, but the other LIGO and Virgo are working well. So it is a very delicate, very, very delicate matter. It's mostly kept by suspending them, but of course, this doesn't solve every problem magically.
Then we have the mirrors are also under vacuum.
Yes, exactly. The mirrors are also under vacuum. Everything where the laser travels is also under vacuum. The mirrors are inside some very, very high towers. And all those towers that contain the super attenuator are all under vacuum.
And then we have Is not LHC in Geneva a bigger vacuum device than like Virgo?
Yeah, actually it is not, because the part that is in vacuum at CERN is not the very, very big part that you see in pictures. It's the accelerator part. So actually the vacuum volume of Virgo is bigger than the one at CERN. Okay, we don't have any more questions. So same thing that we did before, we will now move on to the next step. This one will take a bit longer. So before we said a couple of minutes, and actually maybe it took 30 seconds. Now it will take a couple of minutes, but we'll be back and you can think of other questions if you have them in the meanwhile.